I realised that this Venus story has been around for a little while now. um, and I know that in the UK Planetary Forum, it spans a lot of people, but I know that one of the big things about the UK Planetary Forum is to really promote and encourage the younger members of the community as well. So I'm going to start today a little bit by telling the story behind this as well as the science, because one, it's nearly Christmas, we're all quite tired, it's been a long year, and two, I think quite a lot of what happened around the media, what's happened since, is quite an interesting part of the story of what happened. So let me change sides, that's good. So I think the very first important thing to say is I think this has been one of the most exciting things I've been involved with in my academic career. Jane Greaves, who's a professor at Cardiff that some of you may know, is just an outstanding leader. Excuse me, I'm going to cough. And really has led the team in a very inclusive way, a very equal way, and a really interesting way. It's been a really good example to me of how to do good science and to work well as a team. And this picture, I think, encompasses that, because it is the diversity of the team. It includes the telescope operators, without whom we would have never have got to this point, the data reduction specialists, without whom we'd have never have got to this point. We couldn't just, as scientists, in any way, shape or form, do this on our own. It was very difficult observing. And I think that that is illustrated by what's happened subsequently a little bit, which I'll come to later on. But also, I think it's important, because this is the UK Planetary Forum, to realise that the team had very diverse backgrounds. So I've listed them at the bottom, but I think it is quite important that sometimes these big science advances happen by really having quite a diverse team involved. So I'm a small piece in a big cog, and I'm here today representing all of these people, all of whom have made very, very important contributions to getting to this point. And contrary to what you might think, it also didn't start with that day back in September where we had the press release, or some of the embargo breaches which happened a little bit over the weekend beforehand. It was quite a long story, and when I was writing this talk, I kind of looked back, because I thought it was quite nice as well to see where we started, and I found one of the very first emails about, oh, we had some observations and I think we might have something, where Jane sent the very first, oh, it looks like we've got a line here, and I'm going to, she actually sent us about a 14-page document to try and convince us that the line was real. So it wasn't, oh, here's some data, let's quickly get there. It was a very long story. And then when we had the ALMA data, it was like, oh my goodness, I think there's more of something. And actually there are some things in the ALMA data that never made it to the paper, because we were trying to look not just at the issue which we did publish in the paper about where the phosphine might be, but actually whether there was difference between the day and night, between the solar limb, where we were actually seeing the signal come from. And so there were lots of pieces of data flying around the team which were related to whether we saw day and night and other things. And of course, because we were using submillimeter band passes, we could also look for other lines and check our analysis techniques and what we were doing, not just against how we were seeing things in the region where we expected to see the phosphine, but also in the region where we expected to see other lines that were known and had known intensities on Venus. And HDO was one of those big calibration lines that we used, not a calibration line per se, but to calibrate our mechanisms and our thinking, both with the sort of polar mid-latitude questions and also with the day-night questions, which I've shown here. And I'm whizzing through this because it's not really the science, but I wanted to give some of the people a feeling. Now, I counted yesterday how many emails have occurred in my inbox relating to this project since the very start. It's only 876, all of which are read. But one of the things I have to say is we obviously had to race against the proprietary period, because once we had the ALMA observations, we had 12 months. And actually the paper has been in multiple versions. So I think also, again, this is a useful part of the story for younger scientists to realise, is that if at first you don't succeed, keep trying, is really important. Because we made a version of the paper, submitted it to Science, who were not skeptical but were worried about the impact and decided to reject it. So then we rewrote it for Nature Astro and they were happy to accept it, and it's been quite a long journey, over a year, just to get the paper accepted in the first place. We've had about 26 telecons. That's before the paper was published. Since, we've had a lot more and a lot more email traffic. And there are 19 scientists involved. Now, that's not maybe a huge team, but that's quite a huge, where everybody was constantly questioning everything, questioning each other. There was a lot of intense debate where we were really questioning what was going on. And as I've said before, really carefully led by Jane. Now, obviously, we got quite a lot of media attention and we anticipated that might be the case and tried to deal with that very carefully. And in some cases, we've been praised for how we dealt with that. And in others, we've faced a lot of criticism. But I think we stand by how we dealt with that. We've had quite a lot of community attention, both positive and negative. I have to say it's been one of the hardest periods of my career for very negative and very personal attention. That's been quite challenging, and quite a lot of rebuttal. And I think that that's been very interesting. We've been very, very open as a team. All of our data reduction packages, all of our information, everything was completely available to the community to say, have a go for yourself, see what you think. And what that's led to is quite a lot of rebuttal from various different quarters, which has been quite interesting, and I'll address that a little bit later on. But I think what the press release was it was the start of the end before the start of a journey, and we're still on that journey, and that's quite exciting. Okay, so the timeline actually for this project really began way back in 2007, which I think is quite interesting for, again, for the young people to see. When there was a team of us, Jane, myself, Emily and Dave, who were using JCMT, we were trying to use ground-based sub-millimeter telescopes to observe solar system objects. And what we were really excited by at that point in time was the very first reports by Cassini that there were plumes on Enceladus. And so what we did was we proposed, and we went and observed with JCMT and IRAM Enceladus to see if we could see the plumes from the ground. And what was very interesting was we made some observations in 2007, then we made some more in 2008 and we couldn't see anything at all. And then we made some more in 2009 and we could see something again. But actually already at that time, it's amazing to think now because we have the knowledge, but Cassini didn't know that the plumes were very episodic. So we'd responded to something, and actually it was a real challenge that we were trying to get paper published sort of at that point in time. There wasn't much data. There was a lot of data from Cassini. There wasn't a lot of data in the literature at the time. It wasn't very easy to get a hold of that data or into that data if you weren't in the team. And to be honest, it's still not. So that's a very interesting thing for us to think about when we're linking sort of astronomy and solar system science together. Sometimes being outside of the expertise makes it really difficult to use the data. And I think that's kind of part of the interesting story of this Venus story, is how do we link things together? But we did make some observations, and actually we published a paper which was only in 2019 at the end of the day. It took us a long time to, it's not easy and fast to do these ground-based observations in the sub-millimeter of solar system objects and publish the data. You see long timescales are a key part of this. But we actually called the paper, "When is a biomarker not a biomarker?" And we actually acknowledged at the end of the paper the 3 birthdays that were lost to the project. So we were either up mountains or travelling at the time, and that was 3 different members of the team who gave up their birthdays to make sure they were doing science. But what we did was we put my laser pointer on. Let's pop that on. Hopefully you can all see that. So we were observing Enceladus in a short period of its orbit. So this grey line here shows you roughly where the E ring is, where Saturn is, and the A and C rings are highlighted in here. And we had a very large beam, so our beam was basically covering all of this orbit. And what we were trying to do was to see if we could see any of the plume, essentially, within Enceladus, to see if there were molecules coming off. And we had a whole swathe of molecules we were interested in looking at. It's quite entertaining from the top of the mountain, on top of Mauna Kea. We were very tired and very oxygen deprived. And Jane and I successfully found methane on Titan. We did find that one night. And the other night we found the ozone layer of the Earth before we actually started finding molecules from Enceladus. So we were very successfully reproducing science that was very well known, and it took us quite a long time. We were there in person thinking of lots of different ideas. But one of the things we did manage to do was to detect methanol. Now, I don't want to go into all the technicalities of this because I don't think there are many JCMT observers on here. But what's very interesting is one of the things you often see in the JCMT observations is you see a negative response, a reflection. There were various reasons why we saw this. I don't want to go into it, but the most important line to look at here, it's in the rest frame of Enceladus relative to, you see it's not in the rest frame completely, the rest frame of Enceladus relative to Saturn. That's how we had to observe when we were observing a moon. But we had a very clear detection of methanol emission. Now, those of you who know about Cassini will know that methanol is not one of the molecules that was readily detected in the mass spectrometry of a Cassini when it was published. At this stage, it wasn't published, but we were thinking, oh, in the plumes, if there's water and if there's a surface ocean, methanol is surely a good molecule to look for. Now, also, we detected water. This is water. There's a couple of interesting potential features in the water. Water is well known to be in a trailing cloud behind Enceladus, gas phase water. It's starting to feed the E-ring and it's coming from the plumes and being channeled into the E-ring. So it was useful to have detected water. That's always a good sign when you detect something people know about. But the interesting thing was why we detected this methanol as well. And it took us quite some hunting, and I don't want to go into too many technical details. I've popped the same figure here again. But if you were to view this orbit from the top and think about where the plasma of the environment was around Enceladus. So if you imagine Enceladus traveling in this direction, if you imagine Saturn is in this direction, then Enceladus travels through a weak plasma environment due to the nature of the environment around Saturn. And one thing that's well known is this trailing water cloud that actually trails behind Saturn itself, which is related to feeding the E-ring. And by understanding from our water observations what the information was about the cloud in the water environment, and also looking at our methanol observations, what we were able to identify was a very strong correlation between the water and the methanol, which indicated that the methanol was essentially sitting in this same cloud environment. And so that was quite interesting to us, because it was very unlikely that the methanol was being ejected by the plume and then actually just entering into the cloud environment. And what we realized when we ran some basic chemical models was that very likely water and methane were being ejected in the plume, molecules known in the plume. There being a lot of dissociative electron attachment, lots of interesting chemistry going on. And then what's essentially happening is this quite simple recombination reaction, which recombines a radical and a neutral and produces the methanol. And through this little chemical pathway, what we could do is we could show that actually what's happening in Enceladus is we're detecting a molecule, methanol, which you might consider a biomarker or you might not. There's debate, but it really isn't a biomarker, it's chemistry. And I think it's really important when we're thinking about molecules and environments and observing them remotely, really thinking about where they come from and why they come from. Now, many people have asked us many times why we haven't tied our observations together to Cassini data. We've tried very hard. It is really difficult. It's really difficult to get hold of the Cassini data. It's difficult to find whether Cassini made a pass close to or at the same time as we were observing. And also all the Cassini data were at very different heights through the plume. And we're quite sensitive to certain regions and certain depths in the cloud by using submillimeter data. And it actually transpires it wasn't very easy to tie up what we happen to have done from the ground with the Cassini passes. But I think what it tells us as well is in future, when we're thinking ahead to Bepi Colombo, to other missions, thinking about how we could use ground-based submillimeter astronomy commensurate with when we're making other passes and doing exploration is really, really important. Okay. So let's go back to the Venus story. So I wrote a nice long timeline. I don't want to go through all of this, but we started in 2007 and really then another part of the team, who was led by Sarah Seeger in MIT, they independently started thinking about phosphine. And then we really started in 2016, 2017 to think about making observations. And there were many, many observations. I don't want to go through all of these things. Really, a lot of observations, a lot of applications for telescope time. Many of those were rejected. Some of them didn't work out. Some did work out. And then really moving towards actually publishing the paper. And then one of the things we decided to do very early on was we decided to ask the RAS as an independent voice to coordinate the press release. And they did that on behalf of all the telescopes, so ESA, who represented ALMA, JCMT, all the universities involved, for a single press release. Now, that's quite impressive because we had some big names like Cambridge and MIT and Imperial who had involvement in the project. We had obviously the telescopes who had involvement in the project. We had Jane, who was leading from Cardiff, but we really did it as a team all together, and there was an immense amount of work went on over the summer. Now that paid off in quite a lot of hype, as you're probably used to hearing about. For 6 hours, we knocked coronavirus and Brexit negotiations off the top of the BBC website, and we were very shocked to be like the top story. We were covered worldwide. We did, between the team, over 50 live radio and TV interviews. We'd very carefully prepared our briefings. We were careful with what we said, and we pretty much hit all of the main UK stations and Sky at Night. And so we had a lot of exposure, obviously. I think what was also very interesting was Nature. Nature were very good with us, and we really kept the embargo. I know that the embargo was broken by someone, not in our team, but someone, and a lot of false information and leaking information came out. Nature wrote quite a strong rebuttal of this a few weeks later, not us, they did. But I think what's really important is to remember why the embargo is there. And the embargo is there also to protect both the science, but also the integrity of the science, because some embargo leaks weren't actually telling the truth. And also, we'd been really careful. Nature had released the paper, but hadn't released any of the supplemental information. So what was very interesting was when people were being approached to comment, people were making comments about what was missing. And when the paper came out, that missing information disappeared very, very quickly. So for me, it was a very good lesson in learning, and that's why I wanted to say something about it to our young scientists that are here. A very good lesson in learning how things go. Okay, so some cool stuff before we go on to actually doing the science. But there's a composer who is a friend of Clara, who's at MIT, called Dave Ibbett, who has been trying to make a composition using the spectroscopy of molecules in the Earth's atmosphere to make a composition of what the Earth's atmosphere would sound like if you could sonify its spectrum. And because he saw that we were doing this phosphine stuff, he also sonified phosphine. So I wanted to, hopefully this will work. It worked in practice. I think I'll have to take my laser pointer off for a minute. Okay, so hopefully this will work. So first of all, I'm going to play you what the sonification of phosphine sounds like that was done from this spectrum here in the mid-infrared. Here is the sonification of phosphine. Now that goes on for quite a long time, and actually that note and that feeling of the spectrum is quite hard to ascertain. So he also made an arpeggioed version, which I think is beautiful. I'll just play a small part of it just to be quite fun. But I just think it's quite nice when our science inspires artists to do something a little bit different. Oh, excuse me, just let me stop that. And the other thing I wanted to share with you was a poem that was then written by one of my friends, who happens to be the poet in residence at the Scottish Football Association. She had seen everything going on the news, and she just wanted to write how it made her and the people she knew around her feel. And I just want to read this out as well, because I just think sometimes it's quite important to remember what kind of a news year we've been in, and what kind of an impact sometimes a good science story can have on the broader community. So she wrote, "Our world may seem a little smaller now we can't get on a plane, or pack into gigs or football games, or hang out with our mates. Zoom offices feel vacuous, the quiet drowns out the pain of our crumpled rainbowed windows start to leave a bitter taste. As our world erects more barriers to keep each other safe, a clever team looks skywards for discoveries in space. They join heads around Earth's sister, look for answers in her clouds, bright burning ball of questions the goddess shadows as she shines. Scientists, geologists, astronomers unite, shattering glass ceilings in the quest to find new life. So if your world does seem a little smaller, with new restrictions every day, just turn your head full skyward where new discoveries are made. Thank you for being trailblazers and lighting forth the way. You keep asking the tough questions. You make a difference every day." And I thought that was quite a lovely sort of song of hope. But now let's get behind the hype and let's talk about some science. So I hope that little sort of story has given you a little feeling, especially the younger scientists, sometimes the challenges that we go through in passing our science to the media, but also sometimes the way we inspire, and sometimes we shouldn't forget those little things. So phosphine in the atmosphere of Venus. So this is the image I used while you were for advertising this, and the question is, what did we do? So we looked at the lowest the ground state rotational transition in phosphine, which lies in the submillimeter at 1.23 millimeters. It's not necessarily the most highly populated. It's one of the brightest lines. We do need some additional understanding of radiative transfer to know if it's the most highly populated line, but it's obviously very accessible from submillimeter ground-based instruments, and therefore was a real obvious target to go for. What we show here is we show a combination of the JCMT spectrum in white and the ALMA spectrum in orange, which have similar line profiles. And the background image is also from the Akatsuki UV orbiter, which is currently at Venus, showing very nicely those dark streaks in the cloud deck of Venus, which we don't fully understand at 365 nanometers. We did try to see if there was any correlation between the Akatsuki data. We have a member of the team in our team. We did get a hold of the data. This image here is actually from one of the days when we did the JCMT observing, but there was it wasn't obvious enough, so we didn't go down some excessive conclusion lines, but that's some interesting facts. And the line properties, so in the rotational spectroscopy, in submillimeter rotational spectroscopy, line properties tell us an awful lot. They can tell us about pressure broadening, they can tell us about temperature and pressure data. So we can get a lot of information from analysing our lines, and that suggested to us initially that the phosphine concentrations were somewhere around 20 parts per billion, plus or minus 10 parts per billion. So that is basically what we reported. I think that's really important that we state that from the start. So no one expected the phosphine to be there, really, not even us. So you might ask the question, if you didn't expect it to be there, why were you making the observations at all? Well, sadly, I used to also have an image of Spiker on this slide, and I had to take it off recently because Spiker is no more. But there are a number of missions which include JWST and Ariel, both of which are obviously going to progress, which over the next few years will indeed and decades will indeed be able to go and have a look at the atmospheres of exoplanets, and in particular study their atmospheric chemistry, which is really, really exciting because it really starts to give us those very strong links right from what kind of chemistry is happening in our own solar system, to the chemistries that are happening in other solar systems, to the chemistries that are happening in interstellar space. And those missing links that join everything together, I think they quite drive me to do the science I do. So we also know that when these atmospheres are hydrogen poor, phosphine is touted as a biomarker molecule. Now, in hydrogen-rich environments, such as in Saturn or in Jupiter, when we have hydrogen-rich gas atmospheres, it's quite easy to make phosphine. Quite easy, but it is. There's plenty of chemical routes, but it's not so easy in other regions. And so our science question was really, could we test what these next generation of telescopes might see, and how we might be able to detect a biomarker molecule like phosphine in a hydrogen poor environment, and if we could, what is a good environment to go and test that in? And we focused on Venus because obviously it is an oxidizing and abiotic environment, and it would give us a nice upper limit on how much phosphine you might be able to see in one of those atmospheres. So if we can see it, how much can we see, and what's the upper limit? Now, when we go and have a look, what are the questions when we see that we've got a phosphine line? Is one of the big questions that's come up is, are we certain it's phosphine? Now, the answer in our team is absolutely yes. And what I've given here, it's a very long table of numbers, but if I pop my laser pointer on again, there we go. We're all getting better at these remote talks. But obviously what you have down here is a whole range of frequencies that lie within the frequency range that we were able to see with our of interest where we detected the phosphine line. Now here is the phosphine line. Here you can see it's the 1 to 0 transition. Sorry, no, here you can see it's the 1 to 0 transition. And here you can see the error on the central frequency that we might expect to have. And here you can see a whole bunch of other molecules which may have transitions in these regions. Now, a lot of these molecules are certainly not the kind of molecules we would expect to find in Venus's atmosphere, and certainly not huge, large numbers of those molecules. But there are a few, including this one that I've just highlighted here, SO2, in the ground state with a transition from 30 to 31, J transition, which may indeed be present and are known to be present in regions of the Venus atmosphere. So one of the very important things we had to do very early on was rule out that we hadn't just detected an SO2 line. And it's a little bit convolved how we sort of went about this, but I think it's quite important, and I've numbered the way we do this. So in our observations, obviously we made the observations in the regions of the phosphine, but because of the way you work with the submillimeter telescope, you get other regions of the spectrum as well. So in another region of the spectrum, not so far away, but 264.54, so it's not in this region. You see this is 266, but somewhere further up the channel, there is a region where there is a SO2 line, another SO2 line. This SO2 line is actually the 13 to 12 transition, so it's a much brighter transition, it's a much stronger transition than 31 to 32, the J numbers. It's much more highly populated, and so this little tiny region, this little tiny wiggly region here, that's where that SO2 line should be. So we modelled what would this SO2 line look like if it had approximately 10 parts per billion, and that's this little dotted line just here. And then we said, okay, so what about if this line at 10 parts per billion, this little dotted line, if we took that amount of SO2 and we worked out what the SO2 line would look like in the region of the phosphine line, how would it look? And that's this little tiny green line here. So we said, oh, you know what? There could be a contribution of SO2 to this line, so we could subtract it, and then we would get this red feature here. That would be what would be left that tells us how much pH3 we've got. But then what we did as well was we said, okay, let's imagine this whole line was SO2 and we fitted it as SO2. We don't worry about the fact it's slightly shifted. The shift is important, but let's ignore the shift. Let's not worry about that. Let's just fit it with SO2. And then we made a fit of SO2 to this line. And then we said, how big would the other SO2 line have to be? And that's what this red line is here. And clearly we can see that the information in the spectrum that's there for SO2 in other regions of the spectrum doesn't fit with us having all of this line attributed to SO2, which is why we feel very, very confident. This is included in the supplemental details of the original Nature paper, but this is why we feel very confident that what we've detected is phosphine. So assuming we've detected phosphine, the next interesting question was, where is the phosphine? And the ALMA data, which are shown here in a sort of a set of information which is across the planet. Now, it's probably very difficult to see lots of transitions in there. I don't want you to have to see it in too much detail, but you could go and look in the paper if you wanted to. But essentially what we realised was that if we summed all the data in the polar regions, and we summed all the data in the mid-latitude regions, and we summed all the data at the equatorial regions, it was only in the mid-latitude regions that we clearly had a detection of the phosphine. That was clear that the phosphine definitely resided in those mid-latitude regions. We had hints of that very early on. You'll remember in my first few slides that I showed you. But we definitely were detecting it in certain regions of the planet and not others. And so I'm not a Venus expert. I'm much more a submillimeter astronomer than a Venus expert. But obviously we have to go into explaining why this is the case. So my sincere apologies to those of you who are on the call who are Venus experts if I don't get all of this quite right. I hope I do. I hope I've learned enough about how Venus is. But this is a nice image that was provided to us by Lewis Startnell. And obviously what we have is we have the surface of Venus, and then somewhere about 45 to 60 kilometers up, we have these cloud and haze layers. And in particular, in these cloud and haze layers, we have these super winds. We have these winds moving really, really rapidly, rotating around the planet, really very high velocities. But one of the things we can tell, if we just move over this side for a moment, is Hiedo, who's one of the Japanese collaborators on our project, produced this very nice image showing where the atmospheric temperature of Venus is against the altitude. And obviously we know at the surface it's incredibly hot, and the atmosphere of Venus cools as you rise, and then it has a slight inversion. It's a little bit different to the atmosphere of the Earth. And obviously the pressure gradient changes as well. And because of, as I said before, submillimeter lines being able to tell us something from radiative transfer models and from line profiles about pressure and temperature regimes, we could confine our line to being in an environment where we were somewhere in a reasonably temperate zone, where the temperature was somewhere in an Earth-like kind of temperature, maybe 20 to 50 degrees centigrade, and certainly in a pressure regime where we were in a pressure which was not dissimilar to the pressure at the surface of the Earth, a few bar or so. And so we were somewhere in this cloud deck at 45 to 70 kilometers up, and that's where the phosphine signal was really originating from. And then we asked ourselves the question, well, if we're in this region, how can it be that the phosphine is predominantly in the mid-latitude regions? And what's quite interesting is, unlike on Earth, where the concept of a Hadley cell circulation only really works in a tropical environment, and we have much more complicated cycles which are dredging material from near the surface up into the atmosphere and back down again in a very simple concept. The Hadley cells, the circulation of material which is occurring up into the clouds and back down again to the surface on Venus, is really spanning this mid-latitude region. So we said it seems that the phosphine is entrained in the cloud deck region, somewhere between 45 and 66 kilometers, and it's really entrained in these Hadley cell regions. Okay, so one of the things we're definitely not doing is claiming we found life on Venus. At no point does the paper say we found life on Venus. I think that's another really important thing to say. But the question is, how can we sort of chem-splain where our phosphine comes from? So bearing in mind we didn't really expect to see it, we went, and one of the things we did between the very first detection 2016 and all the way through to when we published, and actually still, is we keep having questions about where could it come from. So a number of members of the team, again not my role in the team, but a number of members of the team did a lot of modelling of how we could possibly generate phosphine. And we really looked at a lot of different methods. We looked at whether meteor or comet delivery could work, whether lightning could work, photochemistry, atmospheric chemistry, volcanoes, even if dust pulled up from the ground could include metal phosphates, which could then react with sulfuric acid, which is a common way we produce phosphine on Earth. And every single one of these, if we put in all our known chemistry, basically produced around 10 to the 4 times too little phosphine. Is someone trying to give me a time warning that I can't see? I can hear someone, so I'm keeping an eye on the time. Okay. So clearly, one of the things we also learned from our photochemical modelling is that the lifetime of the phosphine, even in the upper cloud decks, seems to only be about 4 or 5 hours. So it could be very temporal, but it seems we detected it. So that must mean there must be a replenishing source somehow. And that's also because sulfuric acid and photons destroy phosphine quite easily. So the first thing we said is, oh my goodness, what chemical process are we missing? What don't we understand? Why don't we understand it? And so one of the ways we looked at what this might be is we said, well, let's have a look at how phosphine is made on Earth. And for phosphine in the atmosphere on Earth, there are 2 main sources. One is man-made sources. Predominantly, the breakdown of concretes by acids generates phosphine, and the other is biological. So it comes from certain microbes releasing material. So what this gave us was it gave us some quite interesting ideas or hints, given that we couldn't like reinvent the chemistry of Venus's atmosphere. We were pretty certain there weren't little green men on the surface of Venus breaking down pieces of concrete and creating some phosphine in the atmosphere. So we asked ourselves the question, okay, what if? We don't know the answer now. We're going to have to put it out there for the wider community to solve the problem. It could be a problem that needs solving with the chemistry of the Venusian atmosphere. It could be something else. But what if we guessed? What if we guessed that it was biological for some reason? And how many microbes would we need? And is it even feasible? And this is really where Sarah Seeger's team and the team that are really astrobiologists come into play. Again, not my area of expertise, but this really has been a team effort. But obviously we do have some models and some understanding from the story we have on Earth, that we do understand that we can get airborne organisms that can be incorporated into the cloud decks and progressively, I need my laser pointer back, there we are, and then progressively be rained out or fall out and brought back to Earth again. So we also have an understanding, which is what this figure here from Sarah Seeger shows, that spores and microbes can go into dormant or non-active states and then be activated in certain regions. And so there was a sort of paper which independently really of where we were going, but had also suggested that it could be that in the cloud decks where the water content is a little higher, and potentially there was an opportunity, microbes that could have been shielding at one point in time could then become activated again, could then release the phosphine and come away again. Now all of this goes into the realm of speculation. We have no evidence for any of this. It's all theoretical. It's based on what we do and don't understand. The challenges for all of this are, of course, that even in the cloud decks of Venus, it is roughly 50 times drier than the Atacama Desert on Earth. It's a very highly acidic environment, and we have no known extremophile equivalent environment here on the Earth. So it's very difficult for us to do analog studies as we might with some other environments, although that is being tried by members of this team and some other people around the world. But in order to account for the amount of phosphine we have present, you would need around 10,000 times less microbial phosphine forming mass than you have on the Earth, and phosphine forming microbes are not a big part of the microbial mass on Earth. So numbers are possible, but you know, it's very speculative, and obviously it's clear that we don't fully understand the abiotic chemistry of Venus, and certainly because the phosphine is there, what we have is something we don't yet understand, which is great news for science because it gives us somewhere to go on to. Okay, in the last few minutes, I sort of wanted to preempt some things because I think it's also quite important to see what happened since the paper. So I've sort of told the story of the paper and told the story how we got to the paper. And I think I wanted to finish off by the since the paper kind of side of things as well. So I checked this morning on NASA ADS. There are now 6, I think one's in press, but there are now 6 papers published since our original paper, which have followed on. 4 of those are, well, 3 of those are really following on from our data, specifically saying this could be right, this could be wrong, why is this right, why is this wrong? And well, I think it depends on when you did it. This morning there are 9 papers that are in submission, in review, in not yet absolutely refereed. There were more at different points in time. Some have come and gone very quickly, but certainly it's started a debate and started a conversation, which I think is very interesting. And I just wanted to look at a couple of those. So this is oh, there we go. Oh, this is my phone going off. That doesn't need to happen. This is some work that was done looking back at the Pioneer Venus data to try and suggest, oh, definitely there's phosphine present, and that probably means that pH3 is present. I think it's had a lot of debate in the literature. I don't want to debate what other people are saying. I just think it's quite interesting that what we've done is, remember I said it's the start of a journey. We've started people having a think about what didn't we look at in past data, what are the opportunities. We might have more opportunities. We're working with the Bepi Colombo team, not this flyby, it was too soon, but the next flyby, there may be a chance to do some science as we fly past Venus and have some think about things. But here's a paper that said, oh, we think there's phosphine. And then there was another paper which started off as saying there's no phosphine, and then it's moved itself to there's an upper limit, which looks in the infrared. Now, I think it's very important to understand the difference when you analyse and read this paper between what a submillimeter line is, which is a rotational line, which is very clearly identified with a whole quantum transition of a molecule, and one single infrared line, which is one row vibrational transition. So these guys went back and looked at some of the Texas data from the IRTF. There are obviously a lot of CO2 lines in the spectrum, including this enormous one here. And there are a lot of pH3 lines, 3 pH3 lines, transitions in the infrared that lie in this region. One of them lies here, which is right underneath this telluric water line. The telluric line is not removed from the spectrum, but the guys do an analysis underneath the telluric line to say how much phosphine could be hidden under there, still match the CO2 that's present, and not therefore be seen as a component that's how much of it would we expect to see. I think personally, because I do a lot of infrared spectroscopy as well, it's very difficult from an infrared telescope to do analysis in the region of telluric lines, but this is now a published paper, and what these guys have done is placed an upper limit on the phosphine at about 5 parts per billion from the infrared. They can't see that there from the infrared data that there's a distribution. In fact, they think that most of the phosphine is sitting in one polar region. So this is a very interesting paper. That's there. And then obviously those of you who've been following NASA ADS will see that some people have said, no, you haven't detected it in JCMT. And some people have said, no, you haven't detected it in ALMA. I think that's very interesting because one of the interesting challenges that happened with the ALMA data was that because we really provided all our data reduction programs, all our analysis and all our final data, some people have chosen to pick that up and work with that over the last couple of months and rebuke our findings. Some people haven't. But what's very interesting is no 2 papers that have looked at any of the JCMT or ALMA data have exactly done the processing as we did. Now, I have to say, we have a team who are very used to processing exoplanet data. There's people in there used to processing astrochemical data, people used to processing extragalactic data. And I have to say, none of us realised that when we process solar system data from these telescopes, it's a whole different ballgame. And I have to say, the teams at the ESA, ALMA and JCMT data reduction centres, with the ALMA data reduction centre, actually, we've used the European, the UK and the North American centre. They've actually changed their calibration mechanism as a result of the observations we needed and did. And very recently, the ALMA data got pulled for a little while, which everyone thought was suspicious, but that was because the ALMA teams were doing things with it, not us. And very recently, we republished the data. So this is the original data that was in the ALMA data that was in the paper. And this is now the revised data. You see the line is a little weaker now. We're at 5 parts per billion, not 20. And this is because through the calibration processes and some of the challenges we had with baselines and moving baselines and subtraction, some of the technological issues that I didn't want to go into too much detail here, but we've managed still to identify that we have got an unequivocal detection, show it's statistically significant, and also show that we need to have all of the data in our analysis to really be able to extract these difficult things. So I want to finish by just summarising to give everyone a bit of a chance to ask me some questions. I'm sure there will be plenty. But very important thing, just a brief recap. So we are not claiming we found life on Venus. That's very important. What we are claiming is that we detected the phosphine 1-to-0 rotational transition. That lies in the submillimeter at 1.123 millimeters. And now we're at about 5 parts per billion. You'll notice the 5 parts per billion pretty much, not quite, but almost lies within our error bar that we had before. So we've revised down a little bit how much we have. You'll recall, though, that when we were trying to explain why the phosphine was there, we were around 4 orders of magnitude out on being able to explain. So we haven't reduced our phosphine detection by 4 orders of magnitude, only a factor of 4. So there's still a big difference between a factor of 4 and 4 orders of magnitude. We still can't fully explain why the phosphine is there. We don't know whether it's related to not understanding the chemistry or other things. We do know that it's confined to the cloud deck regions and probably transported there by the Hadley cells. And finally, we really are left in an open-ended point. There are very likely abiotic processes we don't yet know about, which would explain why the phosphine is there. Or maybe we can speculate there could be biological processes, but that's going to require astrobiology and our astrobiology colleagues to question it. But if we come back to the original aim, which was, might we be able to detect phosphine in the atmospheres of exoplanets, and what might that mean if they are oxidizing environment, not reducing environments? What does that detection of phosphine mean? Thank you very much indeed.